In May 2024, astronomers pointed the James Webb Space Telescope at a tiny patch of sky, no bigger than a grain of sand held at arm's length. They were searching for faint whispers from the cosmic dawn. The first galaxies born in the aftermath of the Big Bang, more than 13 billion years ago. What they found shattered everything we thought we knew. There, in the data, glowing impossibly bright through 13.5 billion years of cosmic history, was a galaxy designated JDS GSZ 14-0. It existed just 290 million years after the Big Bang, a cosmic infant that should have been small, dim, and struggling to form its first stars. Instead, it was massive, bright, impossibly mature. It was shining with the light of hundreds of millions of stars, as if it had been growing for billions of years. Except the universe itself was barely 300 million years old. When the spectrum was first processed, there was unambiguous evidence that the galaxy was indeed at a redshift of 14.32, shattering the previous most distant galaxy record, reported the Discovery team. Seeing this spectrum was incredibly exciting for the whole team, given the mystery surrounding the source. But JDS GSZ 14-0 wasn't alone. Over the past 2 years, the James Webb Space Telescope has discovered hundreds of galaxies in the first 650 million years after the Big Bang. And the more astronomers look, the more impossible the early universe appears. Galaxies are too big, too bright, too organized. Black holes are too massive. Stars are forming too fast. The universe, it seems, didn't follow our script. Something extraordinary happened in those first 400 million years. Something that challenges the standard model of cosmology. Our most successful theory of how the universe evolved from the Big Bang to today. Something that suggests the universe's infancy was far stranger, far more violent, and far more productive than we ever imagined. This is the story of cosmic dawn, the birth of light, the epoch when the universe transformed from a dark, featureless void into the sparkling cosmos we see today. And according to James Webb, we got almost everything wrong. To understand what makes Webb's discovery so shocking, we need to go back to the beginning. 13.8 billion years ago, the universe exploded into existence. In the first trillionth of a second, it underwent a period of exponential expansion called inflation, swelling from smaller than a subatomic particle to larger than a galaxy. Matter and antimatter annihilated each other in unimaginable fury. Quarks combined into protons and neutrons. The universe was a searing plasma, hotter than the core of any star. For the first 380,000 years, the universe remained opaque, a fog so thick that light couldn't travel more than a tiny distance before scattering off free electrons. You couldn't see anything. The cosmos was blind to itself. Then, as the universe expanded and cooled, temperatures dropped below 3,000 Kelvin. This was cool enough for electrons to combine with protons, forming the first neutral hydrogen atoms. Suddenly, photons could travel freely. The fog cleared. The universe became transparent. This moment, called recombination, released the cosmic microwave background radiation, the afterglow of the Big Bang that we can still detect today with telescopes like the Planck satellite. This light has traveled for 13.8 billion years to reach us, stretched by cosmic expansion into microwave wavelengths. But transparency didn't mean light. With recombination came the Dark Ages. For perhaps 100 to 400 million years after the Big Bang, the universe contained no stars, no galaxies, no light sources of any kind, just vast clouds of neutral hydrogen and helium gas, slowly clumping together under gravity, drifting in absolute darkness. This was the universe's childhood, dark, quiet, waiting for something to ignite. Somewhere in those primordial gas clouds, gravity was working. Tiny density fluctuations, quantum ripples from inflation, now stretched to cosmic scales, began to grow. Where the gas was slightly denser, gravity pulled harder. More gas flowed in. Density increased. Gravity strengthened. Eventually, perhaps 100 to 200 million years after the Big Bang, some clouds became dense enough and hot enough for nuclear fusion to begin. The first stars were born. These weren't stars like our sun. Theory predicts they were monsters, population 3 stars, made purely of hydrogen and helium, with no heavier elements. Without metals to help cool the collapsing gas clouds, these stars formed huge and hot, 30 to 300 times the mass of our sun, millions of times brighter, burning blue-white with surface temperatures exceeding 100,000 Kelvin. They lived fast and died young. The most massive burned through their nuclear fuel in just a few million years before exploding as supernovae, synthesizing the first heavy elements, carbon, oxygen, iron, and scattering them into space. Their explosions may have triggered more star formation in surrounding gas clouds, seeding the universe with the elements needed for the next generation of stars. And crucially, these first stars began producing enormous amounts of ultraviolet radiation. This UV light had a profound effect on the surrounding gas. Ultraviolet photons carry enough energy to ionize hydrogen atoms, to strip away their electrons, turning neutral atoms back into plasma. As more stars formed and grouped into the first galaxies, they created expanding bubbles of ionized gas around themselves. At first, these bubbles were tiny, isolated islands of ionization in a vast neutral ocean. But over hundreds of millions of years, as more galaxies formed and shone, the bubbles grew and eventually merged. The universe underwent a second phase transition from neutral back to ionized. This era, lasting from about 400 million to 1 billion years after the Big Bang, is called the Epoch of Rionization. It marks the transformation of the universe from dark and opaque to transparent and bright. Rionization is one of the last major phase transitions in cosmic history, and one of the least understood. James Webb was specifically designed to study this epoch, to see the first galaxies and stars that drove reionization. What it found has astronomers scrambling to rewrite textbooks. The James Webb Space Telescope launched on Christmas Day, 2021, after decades of development and multiple delays. It's the most powerful space telescope ever built, with a primary mirror 6.5 meters across, over 100 times more sensitive than Hubble, optimized specifically for infrared wavelengths. Infrared is crucial for studying the early universe. As light travels across billions of light years of expanding space, its wavelength stretches, gets redshifted toward longer, redder wavelengths. Light that was emitted as visible or ultraviolet by the first galaxies arrives at Earth as near-infrared or mid-infrared radiation. The farther away an object is, the faster space is expanding between us and it, and the more its light is redshifted. Astronomers measure this using redshift Z. A galaxy at Z equals 2 has doubled its wavelength. Z equals 10 means tenfold stretching. The highest redshifts correspond to the earliest times. Webb can see galaxies out to Z, approximately 20 or beyond, corresponding to just 200 million years after the Big Bang. It's like looking at baby pictures of the universe when it was barely 1.4% of its current age. In October 2022, just months after Webb began science operations, it captured its first deep field images. The Sears survey revealed dozens of candidate galaxies from the first billion years. In early 2023, Webb's NIR spectrograph obtained detailed spectra of many candidates, confirming their extreme distances. And that's when things got weird. According to the standard model of cosmology, galaxies form gradually through hierarchical assembly. Small clumps of dark matter attract gas, forming dwarf galaxies. These dwarfs merge into progressively larger galaxies over billions of years. The Milky Way, for example, assembled gradually from smaller precursors and is still consuming dwarf galaxies today. This model predicts that early galaxies should be small, dim, and slow to form. At Z greater than 10, we should see mainly dwarf galaxies with millions to tens of millions of stars, irregularly shaped, with low metallicity and chaotic structure. That's not what Webb found. In 2023, multiple teams reported finding massive, surprisingly bright galaxies at Z equals 10 to 14. Some appeared to have stellar masses of 10 billion solar masses, as massive as the Milky Way, despite the universe being less than 500 million years old. When we got the first glimpses of galaxies in the early universe from James Webb, we were expecting to find galactic pipsqueaks, explained Catherine Chworowski from the University of Texas. But instead, we found what appeared to be a bevy of Olympic bodybuilders. Some galaxies appeared to have grown so massive, so quickly, that simulations couldn't account for them. Initial calculations suggested these galaxies contained impossible amounts of mass. If their brightness came purely from stars, they would need to have converted essentially all their available gas into stars with 100% efficiency, something that violates everything we know about star formation. Some researchers suggested this meant that something might be wrong with the standard model of cosmology. Chworowski noted, "Were we witnessing the death of Lambda CDM? Had we fundamentally misunderstood how the universe works?" Further analysis in 2024 provided partial relief. Some of the monster galaxies were actually smaller than they first appeared. Supermassive black holes at their centers, actively feeding on gas and shining brilliantly, made them look bigger and brighter than they really were. But even accounting for this, a problem remained. There are still roughly twice as many massive galaxies in Webb's data as the standard model predicts. The universe, it seems, was far better at making galaxies quickly than we thought possible. As Webb's surveys continued, another mystery emerged: little red dots. These are compact, red-hued objects appearing throughout Webb's deep fields, existing between 500 million and 1.5 billion years after the Big Bang. They're incredibly compact, smaller than many star clusters today, yet extraordinarily luminous. Many show spectral features suggesting both vigorous star formation and active supermassive black holes. The combination is puzzling. In local galaxies, supermassive black holes sit at the centers of mature spiral or elliptical galaxies, millions of light years across, containing hundreds of billions of stars. Their mass is typically about 0.1% of the galaxy's total stellar mass, a tiny fraction. But in the little red dots, black holes appear to be as massive as, or even more massive than their host galaxy's stars. In some cases, the black hole accounts for most of the total mass. In QS01, the black hole's mass is about twice that of the surrounding gas and stars, noted one study. In contrast, Sagittarius A star, which sits at the center of the Milky Way, has a mass that is only a tiny fraction of the total mass of the galaxy. How did black holes grow so massive so quickly? Standard black hole growth models can't explain it. If a black hole forms from a 100 solar mass seed and accretes gas at the theoretical maximum rate, it takes about 700 million years to reach a billion solar masses. But Webb is finding billion solar mass black holes that formed in just 500 to 700 million years. This has revived an old idea: primordial black holes. Perhaps, in the extreme conditions immediately after the Big Bang, some regions of space were so dense that they collapsed directly into black holes without forming stars first. These seed black holes would start out massive, perhaps thousands or even millions of solar masses, giving them a huge head start. That the black hole in QS01 grew so much without any star formation taking place points to a case in which it developed significantly faster than the galaxy, explained Marta Voluntari, co-author of a November 2025 study. The little red dots suggest that early universe physics operated differently than today. Galaxies and black holes may have evolved simultaneously, perhaps with black holes forming first and galaxies assembling around them, the opposite of our current understanding. Perhaps the most mysterious discovery concerns the epoch of Ryanization itself. In August 2025, Webb detected something that shouldn't exist: bright hydrogen emission from a galaxy called JADES GSZ 131, observed just 330 million years after the Big Bang. This is shocking because during the epoch of Ryanization, the universe was filled with dense fog, neutral hydrogen gas that absorbs Lyman alpha photons. Any Lyman alpha light emitted by early galaxies should have been blocked, unable to reach us. Yet there it was, bright Lyman alpha emission, shining through the cosmic fog. The surprise finding is challenging researchers to explain how this light could have pierced the thick fog of neutral hydrogen that filled space at that time. The discovery announcement stated, several possibilities exist. Perhaps the galaxy is surrounded by an unusually large bubble of ionized gas, allowing its light to escape. Perhaps the intergalactic medium was less neutral than we thought, with reionization proceeding faster or more inhomogeneously. Or perhaps something about this galaxy's radiation was different. Maybe it produced an unusual spectrum of light that could penetrate the fog. Whatever the explanation, the observation suggests reionization was more complex and dynamic than simple models predict. The transition from neutral to ionized wasn't smooth and uniform, but patchy and chaotic, with some regions clearing earlier than others. Additional observations from June 2025 identified 83 small starburst galaxies at Z, approximately 8, that were pouring ultraviolet radiation into space with extraordinary efficiency. These galaxies, though tiny, produced UV light at rates far exceeding expectations. When it comes to producing ultraviolet light, these small galaxies punch well above their weight, said Isak Wold, lead author of the study. They existed in sufficient numbers and packed enough ultraviolet power to drive this cosmic renovation. Computer simulations suggest that if these galaxies release about 25% of their UV light into surrounding space, similar to nearby green pea galaxies, they alone could account for all the ultraviolet radiation needed to ryanize the universe. The epoch of ryanization, it appears, was driven not by massive galaxies, but by swarms of tiny starbursts, cosmic fireflies whose collective light illuminated the universe. One of Webb's most surprising discoveries concerns what early galaxies are made of. In May 2024, researchers identified 3 galaxies at Z equals 10 to 11 that are surrounded by enormous quantities of neutral hydrogen and helium gas. These galaxies are like sparkling islands in a sea of otherwise neutral, opaque gas, explained Casper Heinz, lead researcher. Without Webb, we would not be able to observe these very early galaxies, let alone learn so much about their formation. Spectroscopic analysis revealed the gas is almost purely primordial, nearly 100% hydrogen and helium, with virtually no heavier elements. This gas is actively falling onto the galaxies, fueling rapid star formation. The gas must be very widespread and cover a very large fraction of the galaxy, said co-author Duroc Watson. This suggests that we are seeing the assembly of neutral hydrogen gas into galaxies. That gas will go on to cool, clump, and form new stars. This is the first direct observation of galaxies feeding, accreting the raw material they need to grow. It confirms a key prediction. Early galaxies grew by pulling in cold gas streams from the cosmic web, the vast filamentary structure of dark matter that spans the universe. But the sheer amount of gas is surprising. These galaxies appear to be surrounded by gas masses many times their stellar mass, far more than expected. Either they're accreting faster, or they're less efficient at converting gas into stars than simulations predict. The discovery suggests star formation in the early universe may have been fundamentally different. Perhaps stars formed more quickly, or in larger bursts. Perhaps feedback from supernovae and black holes was weaker, allowing more gas to remain available for star formation. Maybe in the early universe, galaxies were better at turning gas into stars, suggested Catherine Chorowski. In October 2024, Webb discovered perhaps the strangest galaxy yet, GS-NDG-9422, observed about 1 billion years after the Big Bang. When astronomers first analyzed its spectrum, they were baffled. My first thought in looking at the galaxy's spectrum was, "That's weird," which is exactly what the Webb telescope was designed to reveal. Totally new phenomena in the early universe, said lead researcher Alex Cameron from the University of Oxford. The galaxy's light signature was unlike anything seen before. Typically, a galaxy's light comes primarily from its stars, with some contribution from glowing gas heated by those stars. But in GS-NDG-9422, the gas was outshining the stars themselves. This suggests an environment of extraordinary energy. The galaxy's stars, likely massive, hot population 3-like stars, are producing such intense ultraviolet radiation that they're heating the surrounding gas to tens of thousands of degrees. The gas absorbs UV photons and re-emits them across a broad spectrum, creating emission features so strong they dominate the galaxy's total light output. This galaxy may be a missing link phase of galactic evolution between the universe's first stars and familiar, well-established galaxies, the Discovery team suggested. GS-NDG-9422 might represent a transitional stage, a glimpse of what happens between the first isolated stars and the mature galaxies we see later. If so, it's a window into a critical but fleeting phase of cosmic evolution. The discovery raises fascinating questions. Was this gas-dominated state common in early galaxies or rare? How long did it last? What triggered the transition to normal, star-dominated galaxies? It's a very exciting time to be able to use the Webb telescope to explore this time in the universe that was once inaccessible, Cameron said. We are just at the beginning of new discoveries and understanding. In August 2025, astronomers at the University of Missouri announced the most ambitious catalog yet: 300 extremely bright objects detected in Webb's deep fields, all potentially from the universe's first billion years. Using sophisticated techniques, infrared imaging, dropout analysis, and spectral energy distribution fitting, the team identified candidate galaxies at ZD greater than 10. Many are brighter than they should be. Much brighter. These mysterious objects are candidate galaxies in the early universe, said Hao Jingyan, astronomy professor at Missouri. If even a few of these objects turn out to be what we think they are, our discovery could challenge current ideas about how galaxies formed. Not all will be confirmed as distant galaxies. Some might be foreground objects masquerading as early galaxies. Some might be quasars rather than star-forming galaxies. Spectroscopic follow-up is needed to confirm each candidate's true nature and distance. But if even a significant fraction are real, the implications are staggering. The early universe was far more active, far more productive at making bright galaxies than any model predicted. This abundance of bright early galaxies creates a profound puzzle. Where did all the gas come from? How did it cool and collapse so quickly? What prevented supernova feedback from blowing it all away? Why was star formation so efficient? These aren't small problems. They strike at the heart of our understanding of galaxy formation. The discoveries from James Webb over the past 2 years have fundamentally challenged the standard model of early galaxy formation. The universe appears to have been far more precocious than we imagined. Several possibilities exist. Star formation was different. Perhaps stars formed faster and more efficiently in the early universe. The gas was denser, hotter, more turbulent. Perhaps massive stars formed more easily without metals to cool the gas. Perhaps star formation wasn't regulated by the same feedback processes that control it today. If early galaxies could convert gas into stars at 50% efficiency instead of today's 10%, that alone would produce more massive galaxies faster. Black holes formed early. Perhaps supermassive black holes didn't form from stellar remnants at all. Primordial black holes, created directly in the Big Bang's aftermath, could start with millions of solar masses and grow rapidly by accreting gas and merging with other black holes. These seed black holes would sit at the centers of dark matter halos, helping to attract and retain gas, serving as gravitational anchors for galaxy formation. Galaxies would grow around the black holes, rather than black holes growing inside galaxies. Dark matter behaves differently. Some researchers have proposed that dark matter's properties might differ from standard cold dark matter. Perhaps it interacts with itself weakly, or decays into dark radiation, or has a small but non-zero temperature. These changes could alter how quickly structure forms in the early universe. Alternatively, the dark matter could be fine, but our understanding of how baryons interact with dark matter halos might be wrong. Initial conditions were different. Perhaps the density fluctuations from inflation, the seeds of all structure, were larger or more peaked at small scales than we thought. This would make structures form faster and earlier, jump-starting galaxy formation. We're misinterpreting the data. It's possible that some of what we're seeing isn't what we think. Maybe dust is affecting the observations in unexpected ways. Maybe some galaxies are actually lensed images, magnified by foreground gravitational fields. Maybe the redshift measurements are systematically wrong. Most astronomers doubt this explanation covers all the anomalies, but it probably accounts for some. James Webb is just beginning. It will observe for at least 10 years, possibly 20 if fuel reserves last. Each year brings deeper observations, more spectroscopy, better statistics. Several major programs are underway. JD's continues pushing to ever higher redshifts, searching for galaxies from the first 200 million years. CEERS is mapping large areas to understand how common early galaxies really are. Uncover uses gravitational lensing by massive galaxy clusters to magnify distant galaxies, allowing detailed study of objects that would otherwise be too faint. Ground-based observatories are complementing Webb. The Atacama Large Millimeter Array observes the cold gas and dust in early galaxies. The upcoming Extremely Large Telescope and Giant Magellan Telescope will provide complementary optical/infrared observations, and future space missions are planned. NASA's proposed LUVOIR could launch in the 2040s with a mirror even larger than Webb's, capable of studying the first stars in unprecedented detail. What's emerging from James Webb is a new narrative of cosmic dawn, one where the universe grew up faster than expected. The story now looks something like this. First, 100 million years, dark ages. Neutral hydrogen gas slowly clumps under gravity. The first dark matter, halos form, attracting gas. 100 to 200 million years, the first stars ignite. Massive, metal-free population 3 stars burn brilliantly and briefly. Perhaps primordial black holes also exist, formed directly from density fluctuations in the Big Bang. 200 to 400 million years, the first galaxies assemble. Small dwarf galaxies merge. Star formation is explosive, efficient, converting gas into stars at rates far exceeding modern galaxies. Supermassive black holes grow rapidly, possibly from primordial seeds. 400 to 600 million years. Ionization begins. UV radiation from galaxies creates expanding ionization bubbles. The universe starts clearing. Galaxies grow larger through mergers and gas accretion. Some already rival the Milky Way in mass. 600 million to 1 billion years. Ionization completes. The universe becomes fully ionized and transparent. Galaxies continue growing, but more slowly. Star formation becomes less efficient as feedback from supernovae and black holes starts regulating it. Beyond 1 billion years, the universe we recognize today. Large spiral and elliptical galaxies dominate. Star formation settles into the normal mode we observe in nearby galaxies. This narrative is provisional. Every new Webb observation has the potential to overturn it, but it captures the current state of understanding. The early universe was more violent, more productive, and more mysterious than the calm, gradual assembly we once envisioned. Epilogue: the universe's infancy. Right now, James Webb is observing photons that left distant galaxies when the universe was less than 500 million years old. Photons that have traveled for over 13 billion years across expanding space are striking Webb's mirrors, being focused onto its instruments, their spectra analyzed by sophisticated algorithms and human scientists. Each photon carries information about the stars that emitted it, about the gas it passed through, about the expansion of space itself, about a cosmos radically different from today's. We're witnessing the universe's baby pictures, not the smooth, featureless infant we expected, but a precocious toddler, already walking and talking when it should barely have opened its eyes. The first 400 million years of cosmic history, a mere 3% of the universe's age, witnessed the transition from total darkness to brilliant light, from smooth gas to complex structure, from simplicity to the beginnings of the magnificent cosmic web we inhabit today. And we're only now, with James Webb, seeing it clearly for the first time. What we're learning is humbling. Our models were wrong. Our predictions failed. The universe surprised us, as it so often does. The cosmos is more creative, more inventive, more capable of producing complexity quickly than our best theories imagined. But that's what makes this exciting. We're not just confirming what we already knew. We're discovering. Every Webb observation is a step into the unknown. Every spectrum contains the potential for revelation. The mysteries are piling up. 2 massive galaxies, overfed black holes, galaxies piercing the cosmic fog, gas-dominated systems, efficient star formation, the universe's rapid maturation. Some mysteries will be solved with more data and better models. Others might require new physics, modifications to our understanding of dark matter, dark energy, gravity itself. The first 400 million years are proving to be the most enigmatic period in cosmic history, the age when everything important happened, when the universe transformed from pristine simplicity into glorious complexity. James Webb is showing us that age, and what we're seeing suggests the universe's story is far stranger, far richer than we ever imagined. The cosmic dawn is breaking, and it's spectacular.